3 are equally spaced, let's flip it around and say subset of numbers, and the only thing to know is that they contain a certain fraction of all of the numbers from 1 through n. Okay, so that's a fraction of the universe. Can you guarantee that there will be 3 numbers spaced? Okay, it's just kind of the contrapositive of what we were discussing in the previous slide. So, for example, pick this, then there are 3 numbers which are equally spaced. Smallest delta which will guarantee such a property, but avoid that you will contain equally spaced. Okay, and 3 numbers equally spaced from an arithmetic progression. So that's why I'll call this from now on. And the pre-construction, the greedy strategy, I said kind of hits a bottleneck at 0.63. So something which is polynomially small in this, but this is not the best possible. There's a beautiful solution due to Behrend from 1946 where you can substantially better. You can get a set which is 2 to the minus root log n fraction of the elements and contains no 3 numbers which are equally spaced. Okay. Square root log n seems like a weird number, but it is reason, and it will come up again. Okay, and so this problem has a rich history, starting with this from 1953. We show that any constant set, in fact, any set with density 1 over fraction will contain such a pattern. This was exponentially improved in several works. Listing kind of the papers or works which we, there are lots of other papers which also study this problem. And the best result was due to Bloom and Sisask. Even sets which are slightly smaller than log density, so 1 over log n, 1 will contain such a pattern. Like a small improvement quantitatively to go from 1 over log to 1.01, but kind of qualitatively changes deduced from it, as I'll mention in a second. And what we showed last year was that is actually closer to Behrend's example from 1940. So, you know, we were shaving all these log factors, but minus root log n, that seems to be the right answer. That any set with roughly 2 to the minus log n to the 1 over that exponent has since been improved, but will contain this pattern. Okay, that's the main result. And here, why study this specific pattern question? And just this fits into this general theme in complex and Ramsey theory in particular, where you when patterns emerge without explicitly enforcing just because you have some large constraint. Okay, so for example, in X, especially when you're looking at numbers, 3 is probably one of the simplest, right? And as a corollary of Bloom's or our result, for instance, you can immediately conclude that prime numbers actually contain infinitely many versions, and this follows without using any numbers except that there are enough of them. And coming from a critical computer science perspective, you know, questions like this have tons of applications. They have a direct application to problem in communication complexity. Mentioned briefly, it has connections to matrix multiplication, test codes, you know, parallel repetition theorem, which is what we're working on this problem in the first place. And the techniques, you know, people have looked at this framework of which I'll talk about. This started from Roth's work and for example, Semerides regularity lemma, which is a tool in graph theory and in combinatorics, all in the context of kind of studying this problem, and so 4-term arithmetic progressions and so on. Higher order Fourier analysis was also very instrumental in studying this problem for 4-term arithmetic progressions. So today I'll talk about a new twist or small twist on randomness paradigm, describe how it applies to 3, and then talk about 2 other sort of, you know, applications, one to communication complexity, and to kind of fast algorithms to problem. Okay, so here's the overline. First, I'll talk about the problem and then the applications. So let's start with how to begin to solve this problem. People started looking at this problem. What is the classical technique to do to go over it? Okay, so that I want to take a detour to a simpler problem, but kind of still captures many things that you need to do to solve the problem over integers. So if you think of the question, so I was saying you need a 3-term arithmetic progression or 3 equally spaced numbers. Algebraically, that's the same as saying, I have a subset. The only thing I know about the subset is that it has the integers. I just have a density bound, no other constraint, and then looking for solutions to a specific. The equation is a plus b equals to c. Then the numbers form an arithmetic progression. I want distinct numbers a, b, c from my equation a plus b equals to c. Right? That's our goal. Once I write it in this algebraic way, whether I can study this problem, addition is defined. Instead of looking at integers, I can look for spaces where addition is defined. And it seems natural to study this equation arithmetic, right? And for this talk, for a good reason, as you'll see, on the K3 arithmetic, right? So now is the space of n trit strings, coordinates, and each coordinate has 0 values. Okay, and I have setup. I have which has a delta fraction of the entire. The universe is now all possible n trit. So little n where n is the number of coordinates, and the unequal strings a, b, c, which satisfy the b equals to c, but now it's all mod 3. Every coordinate I need to satisfy this equation, but in some sense we are trying to make the problem, and you can make it actually precise, because satisfying the equation over small mods should be easier than satisfying, right? That's the intuition for why this should be a relaxation or an easier version of the problem. Okay, so that's why this is called, just think of it as mod 3 version. And so does anything change when you kind of switch to modular arithmetic? Actually, before going on, if you think a plus b equals to c mod 3, this if in each coordinate all the 3 numbers are all equal to each other, or they're all completely. Okay, so a plus b equals c if and only if all 3 are equal or completely different. And this should remind you of a game. It's the game of set. So in some sense, we are playing n-dimensional version of the card game set, and you want to try the game set. Don't worry too much about it. It's not important. But in some sense, we are asking how many cards you need to put down to find the set in this n-dimensional version usual game. Okay, so we have this construction due to Beheran from 1946, which had root log n bound, right? And the first thing that changes is that this goes out the window. Beheran's construction really uses the fact that you're working over equations for integers is harder than modular arithmetic. And in fact, several years ago, there's showed that when you look at modular arithmetic 3, where this is called the cap set problem, the bound is stronger. Even sets which are polynomial are guaranteed to contain such a pattern. Whereas in construction said, forget you have to get almost this n or 2 to the minus root log n fraction, even hope to get such a guarantee. Fields or modular arithmetic, the landscape is different. So the proof of this algebraic methods, the polynomial method, don't quite carry to integers, right? For a good reason, in some sense for a good reason, because we know that that strong are false over integers. But all of the other results that I mentioned, and all of those things, Blumen's, their proofs more or less are analytic in nature, kind of as follows. You first develop a proof for finite arithmetic, and then you push it to integers. In a sense, that's exactly what we also do in this work. If you find with much stronger bounds over finite field, and because it's analytic, you can make it, with some extra work over integers. And subsequent to our paper, Blumen's is this part much simpler, much cleaner, and we're able to do this to all finite abelian groups and not just over integers. So today in this talk, I'll mainly focus on the modulus and kind of try to give the main ideas that go into this and kind of push the integer completely under the carpet. Okay. So the proof of the over modular arithmetic has three conceptual steps, and the first part key ingredient, which is the spreadness to mixing, and this will connect to the classical structure versus random with a small twist. I'll tell you what these two things are. And this is where this other two stuff, and this sort of three-step strategy will keep repeating. Look at mix and so this is a twist on the old method. So before talking about, review the old method. What in this paradigm? How were people studying this problem before? So randomness is this dichotomy, or I should really, think of it wishful thinking, your win-win analysis, where you try and say the following. So what is our goal? We have a n-trait strings. All we know is that it has a certain fraction of the universe. Okay. Before I start working, let's do calculations, right? So suppose this set A is completely at random, meaning each n-trait string gets included in my set with probability delta. What happens then? Are we unlikely to find this path to the equation A plus B equals to C? Turns out, if you pick the set at random, you're very likely to see solutions to this equation. In fact, you're likely to see many solutions to this equation. Okay. The reason is that there are many triples which satisfy. Each triple will be present in your set the delta cube. Each one is getting included within, and there are n squared such triples. So as long as delta is like roughly n to the 2/3, n to the 0.66, get many such solutions. Okay. So the set A was chosen at random, and by this simple heuristic calculation, you are going to find many such solutions, many solutions to the equation A. So the first step in the structure versus random sort of technique is to this relation even when the set A is not chosen completely at random. Okay. Close to being uniformly chosen. And so you have to define this closeness. This is kind of the pseudo random case that maybe you'll get many 3APs, many 3 regions by for reasons where what the heuristic calculation suggests. Okay. One. You want to say that, okay, even if I'm close, and of course, if you have this, it's not very useful. You have to complement it with something else. Close to uniform, you're done. But if you're not close to uniform, what do you do? Right. So this is where you're hoping for this dichotomy. You hope that close to uniform, you identify a very specific reason why this heuristic calculation, and that obstacle is nice enough that you somehow kind of do induction. Okay. In particular, you hope that when you're not close to uniform, you have structure emerging, and this structure is nice for the problem. Turns out to be that of finding a subspace space where has than what I started out with, right? So if I'm done, or if I'm not uniform, there is an where the relative density, relatively speaking, more elements than what I started out with. In this affine space, I am basically same problem as before, but I'm in a better condition because my density is higher and my is smaller. So I can presumably use induction or the density or whatever. So either or if not, I'm kind of ending up with a smaller in the problem with better density than what I started out with. At some point, you can hope to win by this. And so if I just want this, then it's easy. I can just pick a single point and say that's my affine. It's useful for doing the induction. So you want to make sure that your pick has. So you want to find a smaller problem where you have more elements than what you started out with, relatively speaking. Is not too small. So you restrict this. You kind of measure the size of this affine space by looking at the codimension. How constraints do I need to add to get this density increment? Okay. So this is called density, increasing the relative fraction of elements that you're starting to do, right? So either you're close to uniform or that's the dichotomy that we are shooting for. If you could do this, what would you do? I have my set A and the universe is the entire possible entry strings delta. If I have 3 APs, I'm done. Otherwise, you say, okay, there is an affine space. Not A restricted to this affine space. My universe only one time, okay? Or you can it as stage by one to kind of not uniform before you get a okay. So that's and if you follow wheels, it's called let's reverse. The over and want to do this dichotomy and get it and going on for integer here induction match induction on density analogs but it exactly, yeah, that's the only reason. So and then you have to keep times to get it. Uniform is far from uniform elements than before. This is analytic algebraic one which doesn't work over. So how can we just calculate almost your stock? Okay. So I'm going to do this argument, and I should say by cheating. Find this note. Very good. This is better because exactly. Yeah. Now this will change based on the problem that. So from find a substitute for, right? This is the second part. We had to close this happens. Right? I'm trivial. I'm going to say that if not be that if you have the definition by saying uniform density increment. So I'll use the word spreadness. Word spread contains a set A D spread if for as long as it's codimension, and I look at this, the relative density is not more than a small constant factor. This 1.01 is a fixed constant, you know, it's a universal constant 1.01. The spread dimension at most, relative density is no more than 1.01 times original density. Okay. So saying that there are no more to be had, do all the density increments that you can first. Okay. Then this doesn't mean we solve the problem. So what we need that is spread. There must contain many. So let's understand, you know, kind of work with it, massage it into. So we have equation A plus B. Instead of this, it has three variable is not necessary. The following. One measures is such that there's some set times A. To get my two set, as long as B lands, I'm happy. I get a solution to the equation A plus B equals to C in A. So study what is, you know, we are to write about this. Should I count, you know, each pairs collide? Does it matter? The right way to is probability. Suppose I pick which and over set dependent the sum x plus 1 times A. If A all we know is best we can hope for is that will disrupt the entire universe. Plan set as long as delta 1 here, you can, because we are so that's a shoot for they're not just a single set is delta, right? Can going on variable or one, the distribution of x plus y, and I would deviate from the older work that you be sure y is close to uniform. Close to uniform distributions makes a some number of them. The blue one is spiky. You get this almost kind of mixes things. So if the convolution, okay, and here by density, what normalized looking at the density function, not the probability distribution. I'm doing this so our ends because the size of the universe changes, so just not size of the universe. So uniform function density 1, so is close to the constant 1 function of closeness will show. Star convolution with distribution a little bit with the circle. So we want to show that a spread set in this A is then the convolution the function, right? Closeness that you need large, or if you want to, you can imagine the x axis here. It's like all the entry strings from the universe and a function, right? As I said, it's a constant 1 function. I could be don't want points with very low. The notion close and low, they're not okay. And set A is when they convert itself is close to 1. All is mixing spreads just or but one mixing operator of convolution is close to its ability that the problem allows you some extra randomness for one mixing operation and the extra one. Okay, and concretely show is A has some relative. I changed delta to 2 to D. The bonds will be somewhat bad, but A has density to my head, and the convolved density is very close, except in a uniform density actually going to be within 0.9 and 1.1 for all small numbers. You can also say the constant one function bounded by constant. All right. So once if you have this, it's easy to show, closure in particular any set, so you will get many solution problems. Okay. D2 we did log down log or 1 over 10 or something. Yeah. Maybe 10. Sorry. So just to summarize this main parts, you're doing this if I'm close to wish to, if I'm far, I identify the same problem in a parameter and that spreadness, meaning in some sense maybe the terms suggested that you're saying I'm spread over the space in such a way that within too many, okay, one-sided notion, right, is an approximation only in one side. You have bound on the density, but only on one side. Either get you a two-sided strong approximation. So talk about convolutions to the randomness critical. You go from this one-sided multiplicative approximation to this two-sided very strong approximation. Yeah. Yes. So now I tell you how you prove this main spreadness implies mix. We're doing both of them at a high. So before this, I'm going to switch to the counterpositive. Okay, counterpositive. The convolved density is far from the constant one function, then you are not spread. It means that if my t is a large, paying attention that it's not real. I switch start the difference convolution. You can make it rigorous. With difference convolution of A with function, then I can space. So the thing to do is to use this. The hypothesis is that this convolved density goes to the constant one function. It errors in some sense. Errors are not close to or below 0.9. Those are the kind of general density. No relation or there is no effect any these two. In particular, I can have only has the value close to 1 exponent, but there may be a lot of points where I'm below 0.1. But for a large class of density, so density positive, this is also have up, okay, and what if it's not just over any density value distribution, it is spectrally positive for your coefficients density itself is a non-negative function. It doesn't say anything about the Fourier coefficient numbers that you have, right? But functions are not. Slide. Why is state by density convolution of something? So we have and difference convolution of conveys nice. If we take the are old Fourier coefficients, but it's complex, right? But solution, but is the we want to use the statement itself, which is so one, and you will have as well as down. Okay, why is this to upward errors important or I can't tell you too much about it without going too intuitively. What look density than in some sense I really want upward deviation. Okay, so this lemma is saying at least you have many where you have options. Now upward deviation, you have to identify the start points which you want to subspace. Okay, comes in. We want to identify some additive structures that have upward deviation, and here I'm going to ignore all of them and talking about it in a very abstract way. Subset of in any group tells you there is some structure set exactly do some algorithm that we can do to find and we call this part sifting. It's also known as dependent rounding, or for this talk let me call this Swiss cheese algorithm. What is the Swiss cheese? Lot of to try and do that is to if the holes move around. Very unlive all portion. Of course, some of their live that is equal. Here the quality type of what it does increases, and that's the safety of the argument. Once you have this, you get and you get this count point. Okay. Inequality density. They don't even the convolution is far the difference. Everything works. No, stuff is more this beautiful follow task much more because we couldn't use the techniques. Again, back to Burgen's very core sets with this attitude. You don't have subgroup. He introduces a subgroup almost work. The main takeaway is that you do this one step in the remaining 5 minutes. Okay, I said it's is for. So the questions A, B, C, they're all verbs. And they're kind of so N, Z, C depends. Yes, they are in X based on function. And to understand, even if there's a population of the in general, because it's example A which is B, and same thing for city which satisfies. So of the product 0, so tool being generally just or you split up this product. You can when spread objects are spreading at subspaces. Here you will, okay. So in particular, it's a pairs of numbers. We made set A which then what you start still like when you go from spread this the matrix operation, but here you just show it to the product AB transpose indicatively constant is what you should expect, which is the new, right? They have matrix product, you know, and you get some Is the same from activity get it certain dependence. Okay, the same sort of, some of the things become more complicated, some of the things become easier. How to look for additive structure. Complexity, briefly say the application to the third part. Communication complexity. You set up, I have some number of players, Alice and Bob. We're not interested in the need or anything else, we just want the need to exchange this dependencies communication. I have Alice gets X, Bob gets Y. The same thing, no one has all the some function. For example, let's want to information problem is harder than 3. Kind of how data science. Except I'm into this. So usually when we think of communication, we say the number is C my number. Communication. Alice X written as Y written on his phone. And Charlie. Alice is he compute is a function of the other two. So Bob is the same. So no one has all the input overlap to get very non-distance in computer theoretical lower bound theory, showing lower bounds. We can is at least quality there. Right? Alice computes function of Bob what function of really not use this to bound, but let me but it can addition important problem. Best each one from one head. Let's say cap. Right. Communication complexity protocol and communicate. New lower bound here, which was shown in this. All right. An application. And you a graph. As the graph means the split of all of the edges are suppose it's just all basically, and you can say if I want to there is a triangle, list all of these terms related or equivalent to each detector. Let's just focus on the trivial cubic time possible. Can you do better? It turns out you can actually do better. Since then, where it takes with itself 3 times, compute the diagonals that will tell me where the cycles in the graph. Subcubic, but people, computer scientists, are not happy with this. Combine it to also make it precise, but I don't think making it precise is that critical. But integral means that you want to matrix multiplication. I don't want to use subtraction. Reasons to do it. That you do dynamic, not do matrix, see the entire graph upfront, and not extend to hypertext. Algorithm, there's nothing for, example. Algebra and been studied before. The best got some savings cubic run savings were like log into the 6. Recent Nick Fisher and Xander and Shaw. There is a comment which gets and the log sort of problem in some sense, okay. Everything, but let me say one. In some triangles, it's really like decoupling, right? I have my addition. Imagine if I see this, and the is a z such that a of yz times a of xz times a of xy is 1. To count the number of triangles, in some I want to count the expectations, just normalize differently. I want to count the expectation and product. This way, this counting or checking if this 0 is easy. Communication complex. So we can hope that we know how dependent products in some cases. This might not for the general graph. So more to kind of use. Okay, and what is decomp of graphs now? Some combinatorics like similarity, and regularity is an analog. Take any word in the language of matrix, the matrix of A. Undirected. This is just a random person. GPT to make it symmetric. Okay, so what is you take and into pieces. You can do this in an algorithm. Really want is interesting, but they able to do this in decompose into few where each piece be cubic, and you can you can in a small multiplicative factor. Dilemmas spirit to some more uniformity weaker. We are which is this sided, strong. The data that you get we have here is quasi-column, summary, three things. The main thing is to use this fact that allows there is like matrix multiplication that should I mean, some of the positivity is switching from overestimation to underestimation place of these places, and that's big definition of spreadness. You're looking deviations, you need to get upward deviation, and how your structure goes back to this string. Open problem, bottom arithmetic progression here. Things that we don't check. Intermediate step, develop a decoupling inequalities. This one depends on three variables. There are some variables or as or right answer at least. Approaching this board arithmetic, at least if you use that we are using. Okay, new which has substantially fewer parts, but hopefully there are more of that.
So when so this was an differentiation which was done by Aldo 80s between what they call distance, where you only worry about the distribution being bigger. Closeness in L is much more demanding. Yeah, and they showed this one notion is the station, well, the other powerful but more demanding.
Okay,
I'll discuss more this so maybe we take a couple of more questions. Anyone has? Yeah.
Could you please explain the developments of the four-term arithmetic?
Sir, at least as far as I know, none of the things that we did for three-term arithmetic progressions other improvement fourth-term, not fourth-term, those are very things that three-term arithmetic progression.
What's the state of the art?
State of the art. I think there's been new. Yeah, and that's not very recent. Yeah, it's like there's not been many state of the art or something. Is yeah, in some sense I would say going from 3 to 4 would be one step. To that 4 is one big leap, the others would follow. It's heuristical. Actually, you can look at 4 A plus was 3D. They turn out we did here, our own variable questions that makes it harder. Variables, it's easier to find solutions, and if you look at is the
you mentioned this on primes. So I'm I hope you're aware of the green tau theorem.
right.
One of the questions, if I remember correctly, in that paper was they were not able to use with the given can method because using you're just using the size of the sets.
I would guess not. If you do things, it's a different problem altogether. But that's a very good question to think about. Yeah, sure.
Since you mentioned the one very famous plus B equals C, how does this analogy?
It's too much. Very to find any help unless it is things. I think you can.
Like for A reset, so it's
Yeah,
really
exactly.
very more. So they had some flavor of pseudo, maybe. Okay.
I mean, thinking have hoping the some use worked out. I should say, several where one is like this two is a tower of log one example, which is example, but still very far. Somehow there's some connection. I think.
If not, let's see. Great. One you rather.
黑洞明明，观测天象，探问宇宙，基础科学由此萌芽，照亮蒙昧世界。万物方程为本，数学家以思考重塑了人类之物理学家掌握分异的能力，理与性逻辑推理的使命，一召开空实伟，基础科学托举无数希望，推动人类文明走向下一次质的飞跃。风云说与怀群贤，为表彰基础科学领域的，为科学家重塑好奇与探索之机，在丘成桐先生倡与合作的基础大而生。大会聚焦理论物理。 理论计算机与信息科学三大全球顶尖群前跟随与文化的搭建交流平台，基础科学未来大会科学奖和前仰世界多国院士及诺奖团。丘成桐先生担任中评审委员，秉持科学规则，严格遵照评量及其重要奖项，为研究之路指引方向，为人类探索未知世界照亮航程。
Over 100 people and their best ideas, and they presented with recognition their work.
I want to greet Congress with the help of all mathematician sciences. I wish a great success to this.
Highly important event. Community. I myself also made many top researchers.
This is a great opportunity for mathematicians, physicists, world to come. Cutting edge. Forward to attend all these exciting talks.
To see the place come together, physical beings. The best we make will set a standard view of fundamental science. Be a very successful event that will be influential to the whole subject.
从古至今，从未知到已知，以有限的人力探宇宙。基础科学不断拓宽人类认知的边界与基础聚会，这是一场顶尖的智慧交锋，让基础科学之光点亮人类的物和多种，云璀璨，黑洞。的天象，探问宇宙，基础科学要了解。物之几何为根？知已知会。理论计算机与信息科学家影响赋予推理的使命，是托举无数推文手风云际会，朔玉流金北京，怀柔燕姬群为重塑好奇与精神，在丘成桐先生倡导下，秉承开放与合作精神，国际基础科学大会应运而生，聚焦理论物理、理论计算机与信息科学 有机引导世界流，追寻前沿科技之深邃，跨越国界与差异，打击交平等。大会颁发基础科学终身成就奖和前沿科学奖、菲尔兹奖等奖座。
Thank you.
同先生担任中评审委员会，持公正的原则，照评审流程，国际界的重要奖项，为青年迈上研究之路指引方向。所谓之事成。
We choose over and they come for their work.
To greet the International Congress will be held by combining both all mathematicians.
So good afternoon. When I saw the title of the talk, I did not just because I know Ramon always gives great talks. Back when I was in undergraduate, Ramon always emphasized the importance of the more developments. So please, Ramon.
Thank you very much, Yuval. Everybody hear me in the back? Okay. We assume so. Very much. It's a real pleasure to be here at this wonderful many going on. I could teleport myself to multiple different things and great. So I'm very happy to have been invited here. I'm going to tell you inequality. Let me tell you very little some prehistory of this. Actually, had a method that I can long talk about. Okay? Trained from doing this. We're going to talk about convex bodies. Okay, so I assume everybody knows what a convex set normalize. Okay. So what is a convex set? It's a set such that if I pick any 2 points in the set, then the line between those points is this. And you know to look at, right? I mean, this is not, doesn't see, I mean, here is in almost any area of mathematics. The convexity in some non-trivial work. That is from the very beginning of the theory, okay? So the first person to really convexity was I mean, he was a child prodigy. He was mathematics in high school in the 1870s, 1880s for theory. Okay, he wasn't working like that, and it was meet about whether there exist non-trivial integer values for which positive definite quadratic forms, right? So know whether there exists. You get these kind of questions using it. Right? So what did he say? Well, let's measure values. Let's do it in the points where of two variables that are integers are just a lattice, right? Let's say the origin is over here. And let's say I have a positive definite. When is, for example, form less? Well, that set is an ellipse, right? So we draw the ellipse. And numbers have this, right? And he realized a large enough volume would contain an integer point. And it's completely stripped the problem of number theory. Think about it, right? And that then came, which is he started asking himself an ellipse. You know, for a number theorist, the quadratic form is very natural because the quadratic form itself is the term. So special about the ellipse. This proof realizes that theorem that of number theory that he proved, the only ellipse was that it was convex. Right? Symmetry, absolute. So this guy that the notion of a convex set is an important one, and he decided to see volumes of convex sets, right? He developed a theory, and he published this influential paper. It appeared in the Mathematics, and uses ideas and notions that you know. They put the foundation of the field of convex geometry. Also, it introduced a problem which played a huge role in the geometry. It led to developments in algebra. Much more about that. But for the purposes of this talk, let me also say that this paper of Minkowski introduced also some problems. And so I'm going to talk this talk. So, the basic idea of how Minkowski thought about the volume of convex. So let me say up front, Minkowski's paper was in R3. Everything was in R3, but I'm going to work directly in Rn. So let's take a bunch of convex bodies. In Rn. Okay. So convex body set. Nothing fancy. If I volume of a this the volume is a polynomial as a function of convex set. The volume, let's plug in a linear combination of these sets. Lambda 1 k1 plus 2 k2 lambda n km. So this is 1 x1 into lambda m xm, such that x1 is in k1. Let's go. Right? Of course, this now the ordinary function of coefficient, right? And it turns out that when you take these to the volume of these lambdas, so you can write this as the sum I1 to n. So this is a homogeneous polynomial, which is the dimension of the space of lambda. And then there are some coefficients. And these coefficients, that they must depend on the bodies k1 to km that I plugged in. It's a very fundamental fact that volume of convex bodies is a polynomial, and it has coefficients. These coefficients, and it turns out these only, but the negative coefficients. And these non-negative coefficients, you know, they show up naturally like this, but they actually very natural geometric meaning. So there are many natural geometric quantities are just variations of these mixed volumes. These are things you know. So volume area, mean width, and many more. I'm listing these three as examples because I'm going to get back to them later, but for example, subspace of dimension K, project, compute the volume in RK. Now average, for example, that's volume. Okay? So quantum. And what are really like qualities between these mixed volumes? And that's what Minkowski did. And so there are all inequality, which I think is called the Minkowski, but of course everything is called the Minkowski inequality, so we call Alexander, which is like quality for mixed volumes. Right? This inequality by Minkowski in dimension 3. Okay? And it does not a direct extension from dimension 3 to higher than 3. Let's not talk about French. But it's you can so what is this? Let me write it down. So we take a mixed volume. So a mixed volume object that has n with degree n. So a mixed volume. In the Alexander-French inequality, there are two bodies that space. The other ones, I'm just both sides of the inequality. And what if I take the square of this coefficient? This is greater. I do this. It replaces by L. This is the inequality. So it kind of looks like a Cauchy-Schwarz inequality, right? These are called, they don't change. And what we change are these first two, right? So I go K and LL, so it's almost like Cauchy-Schwarz. The inequality goes kind of the way. This is a hyperbolic. You would say, why do you just care about two bodies? But you can apply this, the mixed volume symmetric change. So you again, two different sub choices of these two bodies to get order, right? And this is standard stuff, so we don't focus. Log of the polynomials of polynomial. And now the basic question that I'm going to talk about, and this question dates back to Minkowski in 1903. You know, this appears in these stuff. Which is, this is an inequality. When is there equal? At this level of generality, this. So let me try. Let me try to explain what this is about equality cases. What do they mean? What is the significance of that? So I'm going to a very example. It's a little misleading. It looks very okay, but let's do this example. This is the example that appears in Minkowski's original. So we're now in dimension 3. So we're now in dimension, and let's look at a very special case of this inequality, which is, what am I going to do? I have is a convex, any convex. And B is the Euclidean ball. Look at this inequality, K greater B K, or let's say, yeah, K V B B. This K is K, and then I have K. So now the interpretation of this object guy, this mixed volume, the You get. I'm cheating. The constant is actually 3. Okay. Remember which one? Ignore these constants. This area of K. This is the volume of. So happens to be the mean width. For example, here are 3 geometric kind of inequality between 3 geometric parameters. Asking is, okay, we always have, what does it mean? Equality in this inequality. Always know or equal. So if, for example, I chose a body that was fixed, let's say I chose a body. So the volume is 1, and I fix some at the volume 1 and mean width, right? Then I know that the surface area constant is 3, right? Equality, the surface area, right? Bodies. Now, if I didn't have the volume, this is the isoperimetric. It's the volume. And I want, right, we've got children. As in my case. If we just fix the volume, but also, right? So I took a, right, if I fix the volume, it's like this. But what if I forced it to be this one? On average. Then the ball minimizes. Right? So the question is, force the ball to be, right? What would, in volume 1, wider, we will now minimize surface area. You know, I always should be an ellipse or something, not to be. The body turn out to be a ball. Want to make it wider, what do I do? Point out, and I take its convex hull with the ball. Done is like a party hat, you know those little, right? I can rescale volume 1, right? Increase, right? So if I fix it in the mean volume, and it turns surface area. The only one, because what can I do? We're going very good parties, so okay. I can do this. So I can mean with this. That's also a minimum. I can put this as I want, right? So we can go, right, where I put a fractal on the ball. There can be a countable number of them, for example. And of the surface area. These are called cap. And you immediately see that this is very of story. Parametric theory, right? The minimizers are smooth, they have or constant curvature. You know, they have all, right? The minimizers are not unique. They're unique. And the minimizers have different, right? So they have these corners. So they're, and they can have as many caps as variation. Unusual variation. Notice it can be shown. So these are equation 38 and not clear, right? Is that they are equality in 1908, finally proved by both. So for paper that these are only one, and it. That was what was known about. constraint is overlap. Okay. For example, get this line to the caps of this joint are no constraints. I'm only so I'm don't. If you were not doing convex, then of course mean way. I mean, you could just put point a line out of it, right? So this is a kind of very salty, and he found these absolutely remarkable, which he writes in his paper. It's wrote in the first paragraph about terms of the isochromatic inequality. Fascinated by these things, and the site is only a few years finished. It remained open. That's in this very special. It's useful. Even are to understand the more general. As it remained large, it is a problem that appears in convection. And what you see is that people that is hopeless. And it's written the Alexander probably there's so many of them, and there's and I've published the injection. Vector, what is equal, and what would have happened? I don't even know where to look. The injector should look like it's. So we now know that they're actually he got what's before I try to explain. When you prove an inequality, you have a proof of the inequality, you go proof, right? You look what, and then you end up with the proof of polarity conditions on the that all of the convex bodies smooth. So these are very, and in order to prove the inequality of these, right, you can approximate any smooth body. So if you prove this inequality for smooth body, and then you have step one of the proof. Step one of all the cases. You only have one. You first assume equality when the bodies are smooth. There's sign of the inequality. So they are homogeneous cases where K is equal to is that the fact that those inputs to are highly smooth. Where is it happen when the body, right? But the entire principle behind when the bodies are smooth, they're it's it's kind of a strange chicken and egg problem. So that's equality you'll never see. This works with elliptic operator. If you so any everything. What encodes reason these lies are precisely because standing this really is the rise in intervention inequality. Singularity. They're analytic singularity. So its bodies, they're smooth. The exact pattern of the boundary. Nasty objects. And work with such objects inside to work with in very singulars and things like this. Right? It becomes extreme analytic side. Okay. Even if you were which have a finely combinatorial object. Objects receive, so they're not so bad. But we're playing what these are going to do. But it turns out that that's because n minus 2 convex bodies, and each different, and it's the way that the structure of bodies is causing this. Both of these. So with we make these sides, and but we don't know how to put them together. So what is we resolved this sort of problem is understood completely, and resolved part of the problem in the setting where there are no combinatorial singularities. Okay, to combine these two. In this, to write down something, right? And but we result here, and we require very analytic singularities. So I'm just giving you some kind of. All right. So now we've come to. I'm supposed to write down a theorem. Well, you'll have to settle for never. The problem is that predicted to actually write down what they are. So instead, down some kind of with quotes. So, tutorial side. Okay, so what I mean is that these reference bodies are polytopes, convex polytopes. When I say convex polytopes, arbitrary. So then, equality case. So equality equals k minus 2. Very different mechanism. Completely different cases happen. The first of all, the cases that we already discussed, right? So there's translation and scale. The invariant cases have to be invariant, easy ones, and smooth case. The second, I would say, in most cases, relative, the structure of the combinatorial structure relative. of the boundaries of these reference bodies. So each of these bodies at every point on its boundary has a normal cone, right? For each normal cone with directions, it's the combinatorial normal cone that is important. This mechanism too was the of Rolf Schneider. That's the place that was the main instance. To have a complete characterization, we had to add another mechanism that was is the relative positions affine of these bodies. If I compute the volume of a complex body, I'm in dimension n, but minus 1 dimension. Right? I look at the disk. Volume is 0. Right? But mixed volume is 0 if you have. Right? If I take a flat disk like this, it goes like full dimension. Right? It could be these are all lower dimensional and like the subspaces in which they live. Players standing the. And beside the fact that there are many of these, yes, there's a question. What am I supposed to do with it? Beside the fact that there are different superposition, these don't happen separately. Actually, they can, and they do all appear the same. You have to kind of do phenomena when you're trying to. I mean, okay. You look at the linear of the size is for every body. Right? So this depends of those spans. It's something similar over here at the normal code. No, all normal code. So you fix a direction, and then look at the body that contains that given direction. So each of these normal cones mentioned maybe orient about the relative position of normal cones to contain a fixed direction u. Now you have direction. Determine the okay, so asking you to understand what I wrote here. I'm just trying to give a giver of what kind of truths are showing up. But you mean combinatorial in nature. Right? I mean, dimensions, something. Mention these bodies. Yes. Yeah, so fitted. Cap bodies are, of course, not hollow, okay? So they theorem. However, we have a theorem here that's case of also. There is a similar story over there. It's an isotopes, and you will see. The example. So the example of in any equal space where you real combinatorial singularity. There's only, but it's easiest to think about. Looking at V K L C squared equals V L L C. State just a cube, right? and then in L. So initially in L also be, that's obvious. K and L are not an equality case. Now take out the delete example here. Let me delete. Here, this guy. Okay, corner, quarters. Here. Okay, I might use. Maybe it better go here. Oh, I hope you get my point, despite the fact of the impossibility. 3 dimensions. Yes. No, no matter what numbers you cut, it doesn't cut. The thing that matters is that you these edges cut like this also. You don't have to try. Okay, but I'm not allowed to go further. So what happens here? Here, because the reference, so we don't worry about explaining 3. I'm just going to explain 2. The boundary of the body C here determines what are the good directions. The good are not okay. Any normal direction that is not normal to a corner. Normal to this, right? Like here is a normal cone at this point of the body, right? That's not normal to a corner. So if I take it like one that is normal plane that touches the right plane because I have this of an edge, right? And I look at these plane, right? Still there. But if I take a direction that's normal, one of these take a normal to that corner, because here I sliced off the corner, directions that are normal to a corner, direct happens in those directions. So I'm about to differ in the normal directions that are normal to a corner, normal directions that are normal to an edge. Right? Now what happens in this gives general minus, and those are good directions and directions are bad. Right? So you, I want to determine what's good or bad. It the position of these bodies that can. So from the boundaries of these bodies, I can make a rule that tells me which directions are bad. And then what has to happen is that in order to get equality, you have to be the same according hyperplane. All of the and this is just one very, very simple example of this phenomenon. Again, I'm giving a flavor. You normally see what is going on. Okay. No, because if L is a right, there will be always be a normal direction to. It will necessarily be the case that there will be some direction that's normal to an edge. The ball is shorter than the equality. But you K and C are both cap bodies in this case, right? The ball, and you see the ball is the same in all not normal to actually the same. In my last 5 minutes, do I have 5 minutes? Yeah. I want to talk about something completely different. So we're now not talking about the pure combinatoric. People who work in combinatoric count things. That's kind of their job. Problems as certain. I have a sequence. If eta are equal, then ni plus 1 for all. This is a log concave sequence. It was noticed very long ago that in combinatorics of counts of some. So it's kind of was more is now. But kind of a mystery one. And in many cases, these were conjecture. Recent years, there has been in resolving many of these conjectures about it. Let me give an example. Due to Stanley. It's that. Let me write it like this. Is a 6y1, so it's a set of size n, the ordered set. And if I have a partial order relations, right, to make it a complete order, in how many ways can you? X has rank element X, right? Middle of the order. Right? By young, I think, but I have and notice until stats is just a special case of the Alexander. What? Oh, you give me like this with a distinguished vertex. Stanley did. Given P, he cooks K and L. The variance of order such that I can just represent these numbers n volume number of times and L some other, maybe I minus 1 and n like this, maybe the other way around. Okay. You have this representation. Once you have this representation, if I replace KL by KK and LL, that's exactly one where I. It's influential. In years there was Briggs and other proved long-standing conjecture. About I realized is that they don't need to. You could just differential equality directly for these objects. These inequalities are actually basically the proof of the Alexander-French inequality. And the Alexander-French inequality, you get the same kind of. Well, happens equality. What does it mean? What does it mean that equality? That means you have a geometric progression, and therefore, if you understand the case of Alexander here, you ask geometric in the sequence. What kind of progressions you can get? What happened? And the term duties for complete characterization, you would have said, I can see what you meant, where in the sequence they appear, how, which is quite, these numbers, NI, these and one of the fascinating things, let me end with saying this, you know that they show up in many places. The one similar in equality kind of mechanisms here should be universal, and they should situations in some form or another. And this is largely progress on this. It's in there. Very much for you.
To translate three mechanisms and Caucher.
Okay. So this one, this ability on the fence, right? So our theorem applies. You write construction, right? So there's explicit. So if you just plug these here into this theorem, it explains equality. The problem is that it explains when you have equality. Main data translated back when the conditions are not geometric, and that requires work. Okay, so you don't get that for free. Translate to the combinatorial. Require these conditions. Okay, for these, you get basically a system of linear equations. Means for the system of linear equations to have. So there is work interpreting combinatorially. We have for this inequality, it's in our extended differently other inequalities of this kind, where we see, to me, if I carry arbitrary geometry, you have that you can call a lot of freedom. You have here n in these kind of so not that esoterically nothing to do with other stuff. But that to the combinatorics requires work actually requires a case specific general to do this translation.
So classic of Alexander is different, but these insights give you to require smooth ability.
No proof. But proofs of we can have non-trivial equality cases. That's down. And you have no freedom to prove the inequality, right? So it's that you would first have to understand the inequality. There are various, and I prefer some terms. And then there is Chovansky. Different. What Chovansky does is very X geometry and the torque. Right. But Khovansky's hyper not torque. Khovansky's proof geometry. Yes, but we have interpretation of proof geometry, which means that really understood because a generic. I don't want that to be able to talk about it intelligently.
So one of this case was where easy and almost bodies and then false.
I have nothing to say to you. I'm sorry. Connection between those two things.
Because there also just a structure once we exit conjectures because it's true for the ball.
And that's what one of the things that makes these questions fascinating. This is something we can give me a part of the dimensions of the faces. And you know, yeah, it's completely explicit of the Minkowski sums of the faces. So this is something we can by hand. Doesn't matter.
All the C is also poly.
Paul is out not to be a big deal because when and next to a polytope, turns out not something that absolutely so doesn't prove minus
for question.
Yeah.
Praise the elliptic differential to some sort of operator or simplicial complex or something like that.
The analog is just a the difference is where other branch of elliptic operators that capture this situation. We know how to construct them. We just using Friedrichs extension of some, something. So we and thank
不合多心天象，探问基础科学由此萌芽。不致力数为基几方程为本，加以思考为之。我们掌握不可思议的能量。理论计算 体育项目已召开获10位基础科学拓广人类文明走向过于流金金融业绩群贤毕至，为表彰基础科学领域重塑好奇探访神国际基础大会拒绝与3大基础科学与顶尖科学家深跨越国界与学术海探索基础科学未来会颁基础营养世界多诺贝尔菲尔奖得主评审团委员科学公正的原遵照和标准几基迈上路指引方向
which who have done they come and recognition of their work.
Great Congress of Basic Sciences, which will begin this July, but all mathematical science success to this event.
Looking many
This is a great opportunity for mathematicians, physicists, engineers from around the world to come and get together, exchanging. I'm looking forward to.
We are very happy to respond to human beings. We hope that what we may set a standard field of this event that will be influenced to
从未知道以的语基础可宽人界与疆域之极大聚会，这是我们以基的未来。多肉星云璀璨。
Let's welcome the speaker, United University. California X is old and new about 30 cycles.
Yes. Okay, so thanks for coming to my very about the old from 2017 about some of the newer events problem. This all starts kind of with 5 all the geometry. And experimental extremal first prove Ramsey's theorem, and they get good quantitative upper bounds on graph Ramsey numbers. So as their sequence theorem. Last thing that is actually from this 1935 paper, which is polygon theorem. And so the story behind polygon theorem a few years earlier, the following geometry question, which says, oh, suppose you're given an integer n, going to be a minimum integer ESN. Just to have the point in general positions and convex. To be and when I say that your point set is in general position, I mean start off with has no 3 collinear members. For this and the actual existence. And the first so the first proof is the first plane in general, then some convex. And this isn't so, it's just 5 points. So for 5 points looks here, boundary of the convex at least 4 points. And select 4 convex. 5 points over here with points convex hull. The side of this triangle and look at these 2 points. The line must, and so the anterior points, this again would convex. Anytime you have convex foregone. This part right here for 4 uniform. And let's to be this particular Ramsey number. And then they said that anytime you have capital plane and there must be and that's what you could do. Blend points for 4 tuple. Knots in color 4 tuple bullet points are in convex position. 4 tuple has the 2 Ramsey theorem. You use this 5 here, such that every color red, but we just show which means points such that among them must have the color blue. Have a bunch of points in the plane with every 4 tuple is in its position. So the vertices of a convex angon. Okay, so this bounds on this ES. So in particular, due to Erdos 52, this number, it's known to grow at most double exponential. There was by Collins, and then in 2018, moved by for this particular grow super. So unfortunately, this kind of first proof, it's a bad estimate. The second Zekresh gave and the main 19, which is ESN functions at most 2n minus 4, choose 1. Is asymptotically like 4 to the n. And then it wasn't until a little bit later, until 1960, that shows that he's shows here actually they made this conjecture that this ESN function to the n minus 2 plus 1 the conjecture still it has proven to first and is 3 that ES3 is 3 because an assumption have to be and yeah the conjecture paper of sorry Erdos and Zekresh right kind of in the middle of the introduction that Mike have approved conjecture yes much and Zekresh this is the so they proved but when n is it's not known or not this quantity here to the now somebody check and it's still open. Okay. If we go back to Erdos and Zekresh, we switch 4 to the n basically. And then on the upper bounds. And so the upper bound was essentially 4 to the n conjectured value of 2 minus 1. I do kind of solve this error. That's ESN is to the lower bound by showing ESN and so what I plan to do in this sketch of this result, it won't really do some other results. Okay. One of the main tool problem So then the more recent results, actually a fourth of and so this kind of other fourth famous results is famous cups caps theorem. First case, which is 4 in convex, such that if you order the points from left, the slopes of these consecutive segments are increasing. And what a cap is basically this picture here. So the position order right, slope second increasing. So basically, you know, this is a cup cap. About this, about the rest of my talk. And what this after big N then someone either a K cap. Now, if you just simply substitute little n for both K and 2 plus 1 upper bound for ES. And so, in particular, there's a position stronger, which is although it's quite very nice, please sketch that is quantity here. So I'll sketch a construction of a point set. That's, I guess, what it doesn't contain. The recursive usually takes in the plane in general position. That does not contain this one. Extensively points in the plane and without. And then you make these points very low by any slightly above from the first set. And you take two sets like in this new point set you have attained. So basically, this picture here is kind of the construction. But section here doesn't contain larger cups or caps. It does because these 2 point sets here are what's called mutually avoiding. And what points, if I look at the line, any 2 points from this first set, and likewise the line J, any 2 points over the convex. And so point sets have this mutual property. You can take the largest cup from this bottom set, really glue them together to get a rather large thing. And it was kind of clear that this was the problem of this Erdos-Zakarovic problem, which is cups and caps to position. very to go. First, find large clusters, and then sum together the cluster. Okay. One of us, suppose we had in a plane. We have, let's say, this many. We're and settle in convex position. And so, as I just said, and there's ways to simplest or most finding these large clusters is to basically apply a supersaturation argument. And this is saturation arguments. What you can get is this any parameter you can find either or metric otherwise. That if you just and if we look at these, which I'll label these triangles, from this result regions points divided by, and so these are going to be and so all tend to the two. And if we apply this all to these to the but clusters inside of each triangle points from my, because all I've done is basically subtracted this lower order term. So I have these large cluster points, etc., etc. So I can look at one of these clusters. Let's say, know that side of there. You could define a partial order on these points with respect to inside the of P2. So I guess in this example, since we're in three partial order inside the convex hull of P x2. The way you can think about this partial order is that P and Q are going to be comparable. It intersects this red segment down here. And P and Q are being generated by them down here. So I have of T3. I defined a partial order. Now, partial order, I can apply Dilworth's theorem with this parameter alpha. And inside of this cluster, alpha means that if I need 2 points here, it'll segment down or by Dilworth roughly alpha. So I'll either have a chain of i's, or I can apply into each of the other. That means we'll have the anti-chain this one and this one, anti-chain. And in the other region, chains. And so at this point, you can just apply pigeonhole, for example. And you can conclude just by pigeonhole that either you'll have many non-adjacent chains of alpha, or you'll have many consecutive triangles. Consecutive regions with and the one. So therefore, you could just trace it. The triangular regions here, and the anti into the alpha. And so what will happen if we'll have size here, which will turn out to the cups. And so therefore, by the cups caps theorem, if one of these anti has a done, because this is endpoints in convex position. So each of these have these size 2 times n to the 2/3. Many caps of size. And basically, proper. We have these cluster position. What you could do at this point is you basically gather all of these little mini caps to basically each mini cap has size 2 times n to the 2/3. And since there's this many of these mini caps, that means that again we would find. So basically would be done by position. Okay, in case of that, which means max region. So these are my consecutive triangles. And to the one. And so what's nice about these two chains, chain generate by these two mutually settle the 2 to the n and remove the endpoints. Point can constants. You have therefore there's a n direction to the large chain of size bigger and to the third, then done, which means that I can times cap going in the other. argument over and over. So the chain is so in the cup's cap. If I have done, which is n going over, so that either I or by the time I get into the two and the chains roughly are going to be have three inner. And so therefore, or if I number and I cases thing include that there would be that is roughly. Quick questions. That argument that I just gave to have a size of each the situation. Whatever that error term today that we know of is okay. In the last 10 minutes, talk about kind of some newer. We talked about less the status of the problem. Now, so first, fairly classical. A new variant where we polygon problem in next position. In higher and function the main SDN and then somewhere and point complex polytope. Just know good kind of do in RD is you could just simply to the projected dimensional space, but results in the plane. You could just project your points down to the plane, so that the is in and then notice that when you take the pre-image of that sub, will be in so this was observed by actually Valtar and Carly. Around dozen. And so basically what this means experience is also n because that's the bound we have. However, it's believed that this function grows kind of more that Ferretti 3 then function grow of 2 to the root n. It grows on the order to the n to the 1 over d minus. Basically still wide. It's a fact that there are mad quantities. So this was shown by in 2003. Sorry. Okay. This lower bound of 2 to the n to the 1 over d 1, this to the n, which is pretty weak. All we did was just project it down to the this problem. These two young here broke through a barrier by showing that in 3 dimensions, ES3n is at most 2 to the little o n. Then down to 3 dimensions, find points in. So I won't say so much about the actual where these numbers was, just to give you some idea. Because we just went is that they can express Kap's theorem in 3 dimensions. By Cap there and is the position to glue together. I don't know how enlightening this will prove. You can kind of blow out key ideas. We have quantity here. Will be a infinity very slowly. We have capital N points in R3. And so, as I said before, the first thing you will do is in cyclic position. So the cluster of a cyclic polytope. And then what they did is they applied this theorem. And these get to by these 2 points. It's other clusters. And this theorem and Ramsey also shows root is theorem here. And so this quantity here theorem. So what they can have a kind of the comments, and so there you have these of structure of the clusters being of size n over k. Again, its position. Details, but where these numbers roughly get for the log n is better. It kind of broke through that exponent. It's still quite far from which value, so there's definitely problem in the second kind of a recent squared are David Collins and Erdogan problem we didn't come are on a line. And so yes, integer big X. I do point that either L on L little all this phenomenon must contain a big okay. Much was known about this. Yes. Nash plane will helpless problem. We have in your you're done. Therefore, we can there could a trace collinear trace random out of these points. Randomly will be in general position. Once you have kind of the general position, and results that we we work so and so we start allowing collinear from the function collinear, and that was is that kind of correct? And we are able to show L square factor is the best known up. So we have L 2. So in the other direction, construction of for at least one L. I'm sure that just one can be best known up bound from collinear L to change this function much. But unfortunately, how to get rid of this L squared factor to speak this L. Which, and so if you deal with part of the that's roughly speaking world, but it shouldn't.
I have two questions. The first, you mean convex moment curve
Position on the moment curve. Properties of a convex moment. Longer.
Okay.
So when I as points on the moment curve.
Is when some probably means that my maximum thing, but it is defined Ln, which means that
some collinears.
then ability times the other extreme of the probability. So last slide.
Well, this is the last slide.
That this should be L to the should be the it used from L squared to L so the is squared.
A little question. Wow.
Yeah, related to the
Can we believe it? Maybe ones of this and get in because kind of easier because with L have a good answer and L factor and an R the Dilworth wasn't kind of a good read. It came from the proof.
okay, thank you.
Question is higher dimension. On a
Some points.
yeah, on my cases.
Look at
Yeah,
in
higher
higher
dimension.
dimensions, I
Yeah.
really, but yeah, using it to specify general position. That would position in the, but then that's the
there's
藏物合多容，黑测天探问宇宙，基础科学由此萌芽。这是万物之理，数为处即为本。数学家以思考之，家我不可思议。机科学家以想象赋予机器逻辑推理，一朝开获，与无数希望，推动着走向下自觉时代之前，去获怀柔眼肌群必为表彰基础科学领域重塑探索同先生倡导下，于基础科学大会应运而理论计算及基础科学领域科学教师世界流研科技深意大树交流平台，探索科法基础科和前沿科学2菲尔组成评审团。评审秉持真正的原找了要奖，我执意
who have done their and they will be recognized.
It function with helped in all mathematicians, physicists.
It is for scientific community, but to me,
This is a good
to that will be better that a product fundamentals will be so to
科学基础科学会，这是一场以基础科穷间物和多心明观蒙雅烈以数方程学家以思考比我们掌握理论计算机学机器逻辑比一招海获往人类文明走向是大夫第七是基础科激素好奇与省倡导向国际化高理论物理基础科学领域家引领前沿科技界与文化的差异性探索大会吧发研科学组成评担任中评入学严格流程国界的经方向业界成
who have best work and they come up there.
Work on basic science, which can be combining both mathematics, all mathematics.
It's important. I'm
mathematicians, physicists. I'm looking forward.
We are very minds of front objects that we hope that we make that field this will influence and so that will be benefit
地道有探论内认知的边界与疆域等等。 基的未来。贡献和黑洞名测天下，讲论也由此萌之理经方学家的认知。长父语境基础举无论领域学技刘旭怀柔燕其为表剧的重素号作贡献先生王玉和应运我学理论计信息基础科学加真法语化的大数海当成就科技前沿科学